Now, you might want a something to take notes with or something just to write with, so you can do like scratch work. With this Pear Deck, you will be doing some math and calculating some stuff. You might want to have a calculator available. All right. So we'll start this. We get started. All right, so this is our exponential growth practice for today, which is Wednesday, November 18th, 2020. We'll be exploring examples of exponential growth and their different representations, tables, rules, graphs, and context. All right. As always, if you have any questions, if something doesn't make sense, if you would like a better explanation or a different explanation of something that we've seen, please raise your hand, type it into the chat, or simply unmute your mic and ask. All right, I'll be watching all of these avenues. All right, so we're going to get started. I'm going to give you guys a couple minutes per question to respond so that we can kind of keep moving. So here we go. First, this is not a question. This is just a little bit of review. What exponential growth looks like. We've looked at two graphical representations of exponential growth. We have the tree graph, which is crudely drawn right here with our little dots. This is representing starting with one thing, one person, one bacteria, one thing, which then goes to 2. Each of those goes to 2, and we're seeing a growth of multiplying each step or each stage, each level of the progress of the process. We've also looked at what an XY graph looks like. And this is a basic exponential growth curve right here. See that it starts kind of slow and then all of a sudden just skyrockets up. That's essentially what an exponential growth curve looks like when we graph it. This is not for any particular function. That's why there's no numbers. It's just what it looks like. And we can also see this type of growth in a table. And again, in a little table here, we have a horizontal table. We could also use a T-table if we wanted. X is increasing by 1. The output, or Y, is growing exponentially, and we can see that because it's not growing by the same amount each time. Right? It's multiplying by 3 to go from one number to the next. That's exponential growth. If we saw the same increase each time, like +2, +2, +2, that would be linear, which was our last unit. We can also see this growth in symbolic rules, or now next rules. We have our basic kind of like base formula for an exponential function. We have y equals a times b to the x. All right. Whenever we write a letter right next to something within parentheses, that implies multiplication. And we have now times b equals next, starting at a. I've used the same letters on purpose. B is our rate of change, right? That rate of change for B. A is the start value. All right. It's the value of y when x equals 0. A will be. Is there any questions or anything I can clarify about the different representations we have for exponential functions and exponential growth? Okay. All right, so we're going to get started. Here is the first question. Linear or exponential. Select the rules and graphs that represent exponential growth. All right, and in this one, you're going to use your mouse to like draw a circle, or as best as you can, around the things that are exponential growth. Okay. And I'm going to put 2 minutes on the timer. And then we'll talk about it. Make sure you're selecting the appropriate rules and graphs. The rules in graphs don't necessarily match. You don't need to try to match them. We're only just circle the ones that are exponential. Okay. All right. Does anyone want 1 more minute to work on this? Raise your hand if you would like 1 more minute, or just say you want 1 more minute. All right. So here we go. The solution. All right. The correct exponential growth representations are B, C, E, and G. Y equals 2 to the x. Y equals 2 times 3 to the x. The graph of E and the graph G. All right. Can someone tell me why rule A, y equals 2x, is not exponential? Or can you tell me what type of function it is? All right, so Destiny is saying it does not have an exponent. That's one of the giveaways, right? It's in the word exponential, we have the word exponent. And yes, Haquin, excellent. It is linear. It's a linear function. All right. What type of repeated operation is happening in a linear function? What type of rate of change do we have in a linear function? Constant, yes. Consistent, yes. So Jocelyn and Destiny, that's correct. It is constant and consistent, but we have a constant and consistent rate of change in exponential functions as well. They're using different operations. What are the two operations that happen in a linear function as far as our rate of change is concerned? Think of our 4 basic operations. We have addition, subtraction, multiplication, and division. What are the 2 operations that occur in a linear function when we're looking at rate of change?
Adding.
Adding, yes. That's one. What's the other option?
Multiplying.
Not for linear. We end up, so we're doing multiplication, 2 times x, right? But multiplication represents repeated addition or repeated subtraction. Yes, Eileen, subtraction, right? Exponents represent repeated multiplication. right? So the operation that's being repeated is the rate of change, right? The thing that's going over and over again is that consistent or constant rate of change. In a linear function, right, like a here, we're repeatedly adding 2. That's why 2 times x. In b, we're repeatedly multiplying by 2, 2 to the x power. Right, so an exponential function has repeated multiplication, or it could be repeated division by the same number. Linear functions have repeated addition or subtraction by the same number. So that's the major difference. That's the point of this slide right here in this question, is to see the difference in operation and representation. All right. Is there anything that I can clarify before we move on to the next one? Right. Next. Which graph corresponds to the given context? This is a multiple choice. Brian and his 3 friends decide to start their own Pay It Forward campaign. They will start the movement by helping 3 people each. Each person they help will then help 3 people, and so on. Right, so which graph represents that situation? A, B, or C? We'll give 2 minutes for you guys to respond. If you have a question, please let me know. If you have not responded, choose one. You've got a roughly 33% chance of getting the correct answer just by guessing. All right. Before we move on to the solution, what we've got right now, I've got, let's see, 18 out of 20 people registered on here have answered. So we have 6 people for A, 10 for B, and 3 for C. Can I have, okay, someone who answered, okay, thank you, Nicholas, no worries. Thank you for getting here. Are you able to, are you in the Pear Deck? Please try to join the Pear Deck if you can. Yeah, okay, awesome. Cool. So, someone who chose A, can you either unmute your mic and tell me why, or type in the chat why you chose A? Or I can pick someone I know who answered A. Okay, because the number of people is growing faster. All right, thank you, Jocelyn. Anyone else who answered A have an additional reason for A? Where the line intersects after every 3 squares. Okay. All right. All right, so now let's go to B. I have 11 people who chose B. Can someone tell me why they chose B as the option, the graph for this context? That too. All right. So Nicholas, you're saying what Eileen said is why you chose graph B? The rate wouldn't be straight, correct? Yeah. This is an exponential growth function, so we should be choosing between A and B. All right. All right. So B high, right? It increases fast, correct? All right. So here we go. Let's look at the response. All right. So the answer is A. It's the answer. So why was it not B? If we look, how many people are starting the process with Brian? We have Brian. Sure. So if we look at the first sentence of this context, we have Brian and his 3 friends decide to start their own Pay It Forward campaign. So how many people are starting the process?
A total of 4.
Total of 4, right. So the main difference between graph A and graph B is A has a higher starting value. B represents starting with only 1 person. A represents starting with the 4 people. And because we start with 4, it gets to this like 100 level faster than graph B. Essentially 4 times. We start with a multiple of 4 rather than a multiple of 1. We're multiplying by 3 consistently, right? It's 3 people on each level, so times 3 times 3 times 3. But instead of starting with 1 times 3, the whole thing starts with 4 times 3. So we start with 12 people on the first level instead of 4 people. And then it goes to 36 instead of 12, and so on. So it's growing faster, right? And it starts higher. So that was the key thing we had to see, and it's not highlighted. It's not like, it doesn't stick out in the context, so you have to read it carefully. You're welcome, Destiny. Right? The start value can sometimes be hidden. It's not an actual like numeral. It's not a number. It didn't say the number 3, like written as a 3. So you have to find it. You have to be careful. Anything else I can clarify or explain better? All right. Next. So now, I want you guys to type in the now next rule for the given context. It's the same context. Brian and his 3 friends decide to start their own Pay It Forward campaign. They'll start the movement by helping 3 people each. Each person they help will then help 3 people, and so on. So please write your now next rule. It'll be now times something equals next, starting at something. Two minutes. Make sure you're actually using an equal sign. It should be now times the number equals next, blah, blah, blah. Okay, good. And be careful again, this is the same context as the previous question. The start value is not 1. We're starting with more than one person. This is a now next rule, so there is no y equals present in this. All right, can you raise your hand if you'd like another minute to work on this one? A bunch of people are still working. I'm gonna give you all 1 more minute because I see people still working. 1 more minute. All right. Okay. So we're gonna look at the solution to this one. So the now next rule for this will be now times 3 equals next, starting at 4. Some of you had this, some of you guys are working on getting there. So someone tell me, where does the 3 come from? Where do we get the multiple of 3?
The 3 friends.
So we do have 3 friends, but that's not where we get the multiple of 3 from the context. Okay, yes, Nicholas, yeah. They help out 3 people. So each individual helps 3 people. So 1 person, 3 good deeds, right? Thank you. Right, yeah. So I think, so here's another thing that comes up with this. Because I believe, Destiny, that you understood that the 3 people was the 3 people they're helping, right? But what you understood didn't come out in what you said. And this is the thing that happens a lot in math, is we understand something intrinsically, we get it, and we can put it into practice. But when it comes to writing it down or explaining it, it gets lost in translation. And that's incredibly common in math, because we're not used to writing or explaining much about math. We're used to just doing the math. But as you progress through your math education, being able to explain and write it down in a way that actually says what you're understanding is incredibly important. It's that next level of understanding, so to say. And so making a differentiation between the 3 friends and the 3 people being helped by each person is something that needs to be made. We have to be very specific about what we're talking about. So I wanted to kind of emphasize that point. So then, getting back to this now next rule, where does the 4 come from? Right, Jocelyn, thank you. The 4 is the 4 friends. We have Brian and his 3 friends, so there's 4 friends to start. Excellent. Right, and in a now next rule, all I need is the multiplier, right? Because this is exponential, we're doing a multiplier. For linear, we need the adding or subtracting number, right? And the start value. Those are the only 2 numbers we need. Next one. So now, same context again. We're doing the other type of rule that we've done, the symbolic rule. Right? So we're going to write the y equals rule, essentially, for the given context. Brian with his 3 friends. To make an exponent, because I don't know if you have that option within the text editor in this program. If you press Shift 6, you get this little up arrow. Put that in between. Yeah, Isabella, you just typed one in. Put that between the number and the x. Right? That represents an exponent when you can't actually get a superscript. So you press Shift and 6, Eileen. So let me type in the chat here. Shift and 6 at the same time, and you'll get that little, they call it a caret in some typing classes. It's a little like up arrow thing. Yeah. All right. We're going to look at this one. We're going to look at the answer. We're kind of all across the board here. The responses. So let's look at this. So the solution on this, we get the formula y equals 4 times 3 to the x. All right. So, excuse me. We get this rule, right? We have a start value of 4, right? Brian and his 3 friends. The multiplier of 3, right? Each person helps 3 people. And then x is the exponent because it represents whatever level of the process or whatever stage of the process we're on, right? That's the value that gets replaced. The 4 and the 3 never change. All right, the level of the Pay It Forward campaign changes as it goes. So that's why we use x as a placeholder in the exponent spot. In this case, there is no addition or subtraction going on. There are exponential functions that use addition and subtraction somewhere within their symbolic form. We haven't looked at those cases yet. We're not getting there yet because those create what's called shifts in the graphs and representations. We're just not there yet. We're starting with our base, more simple representations. So that's where this gets built. And y is just the placeholder for the number of people helped in each stage. Right. So what can I help explain? Does it seem like we were kind of all over the board on writing the formula? So I'm trying to figure out if I've addressed what wasn't making sense or if there's something else I can explain for you. Okay, we're gonna do one more. All right. So here it is. You're gonna need to use this rule. All right. So now you might need a calculator. How many people will be helped in the third stage? Same exact context. We're looking at the third stage. Remember, we need to use the rule that we just saw on the previous slide. Y equals 4 times 3 to the power of x, where x represents the stage of the process. You got 1 more minute to work on this one. All right. So here we go. Some of you guys got this. Some of you guys skipped a step, so to say. But you're very close. So you're just missing a little piece. All right. Here we go. Like shifting around. All right. Boom. So here we go. We can calculate this third stage by replacing the exponent x with the value 3 in the symbolic rule. 4 times 3 to the third, which yields 4 times 27. So if you got 27 as your answer, you forgot to multiply by 4, which was the amount of people we started with. All right. If you got 36, it's because you only multiplied by 3 twice. You did 3 to the second. All right. And then 27 times 4 is 108. All right. What questions do you have? What can I clarify? Yeah, so we get the power of 3 in this case because we're on the third stage. Now, when we're looking at exponential growth, let me show you something here. When we're looking at exponential growth, right? So let's do a little tree graph here. We start with our 4 people. They're each helping 3 people. They each help a bunch more people. Right? This first level is stage 0. The starting stage doesn't count, essentially as a stage number, right? So then this is stage 2. I'm sorry, stage 1. This is stage 2, right? And then the next one would be stage 3, which I'm not going to draw 108 circles. All right. And this works, right? If I calculate using the rule y equals 4 times 3 to the 0, this gets 4. 4 times 3 to the 1 is just 4 times 3, 12. 4 times 3 squared. 4 times 9 equals 36. And so on. Right, so when we're talking about exponential growth and exponential functions, the first stage, or the starting point, where the exponent has a value of 0, because we haven't done anything yet, we haven't started the process yet, It essentially doesn't count. So when we look at stage 3, it's the 4th level. If we're just thinking of levels, this is level 1, level 2, level 3. The 4th stage is the 3rd, or the 4th level is the 3rd stage as far as like rows of dots in this case. Does that help kind of clarify why we use the power of 3 for you, Nicholas? You're welcome. All right, so we're going to stop here. I have more. We'll do the rest of these slides because we're going to move to a different context for the next set of questions. We'll finish them on next class because I think these are valuable to do. I don't want to just not do them. But for now, it is already 9:25, and I want to go over the discussion board for today. And that, we're gonna go here. All right. So here is what the week looks like in your view. So we're on Wednesday doing our exponential growth. I will update the live class resources. The slides going along with the Pear Deck will be put into the live class resources, as well as this recording of class today. This is our discussion board for today. It is matching exponential function rules, graphs, and situations. All right, so in this first step, we have this big table. We have 4 graphs of exponential functions listed or shown on this one graph, 4 situations and 4 rules. Your job is going to be to match these, the graph to the situation to the rule. Okay? So you're going to have to read carefully. Make sure you get the correct starting value with the correct multiplier. Use process of elimination if you're not entirely sure which one goes with what. Get the ones you can and then guess on the rest. Right? To submit your response, there's this table here. All right? Easiest thing to do, like it says, you can copy the following table and paste it into the discussion post, then complete it. All right? So literally, if you take your mouse and you highlight everything in the table, copy, click into your reply, and paste. It duplicates the table for you. And so then all you have to do is delete the little blank lines and type in your response. All right, once you've completed the table, you'll just hit post reply and you'll be done. Okay? Any questions about the discussion board? Then, as far as the rest of the week goes, we will have a weekly assignment. There will be a CYU this week, which will be posted tomorrow. And there will be another discussion board for Friday, which hopefully will also be ready and posted tomorrow. All right, we'll continue with exponential growth tomorrow, or I'm sorry, Friday. And then it'll be Thanksgiving break. We'll get a week off. Woo. All right. So, bye. All right, so if there's anything I can help you with, please stay on the line. Let me know. I'd be happy to go over other examples or explain something further. Otherwise, you all are free to go. Have a wonderful rest of your Wednesday, and I will see you on Friday.